Pembahasan berikutnya adalah tentang distribusi normal atau sering juga disebut distribusi Gauss ya. Distribusi normal atau distribusi Gauss adalah pola distribusi probabilitas dari variabel random kontinu ya. Jadi ini diperoleh dari banyak data ya yang bersifat random kontinu dan selalu mengikuti pola tertentu ternyata ya. Yang polanya pola tertentu yang normal ya, yang biasa itu disebut dengan distribusi normal atau distribusi Gauss ya. Atau dapat dikatakan ya, setiap variabel random kontinu dia akan mengikuti distribusi normal atau distribusi Gauss ya. Dibedakan atas dua, yaitu yang variabel random ya. Dibedakan atas dua, yaitu variabel random kontinu dan variabel discrete ya. Variabel random discrete. Jadi ada dua variabel random, ada yang kontinu, ada yang discrete. Sesuai dengan namanya, ya, kalau kita punya ya garis seperti ini, maka ini adalah variabel kontinu ya. Kalau kita punya data-data nilai tertentu, di sini, ya ini namanya variabel discrete ya. Discrete itu artinya ya tidak kontinu ya. Sifat-sifatnya selalu bisa kita bedakan ya. Yang pertama dia itu countable, bisa dihitung. Kalau yang kontinu nggak bisa ya, atau infinite. Terus kemudian, nah kalau yang discrete nothing in between ya, tidak ada di antaranya ya. Kalau yang kontinu always something between, selalu ada yang di antaranya, atau ini bisa dikatakan, ini kata singkatnya, variabel kontinu itu analog, yaitu always something between itu analog, kemudian yang discrete itu digital ya, angkanya discrete tertentu seperti ini ya. Oke. Contoh yang paling jelas ya, yang discrete itu misalnya jumlah mangga dalam 1 kilo. Nah, itu ada berapa mangga? Kadang 3, kadang 5, 4 ya, itu seperti itu. Bersifat discrete dan dia tidak ada di antaranya, tidak ada 3,5 jumlahnya kan itu. Tidak ada 2,5 ya. Dia bersifat countable dan nothing in between. Nah, yang bersifat kontinu misalnya tinggi mahasiswa di Indonesia, ya, misalnya gitu ya, atau tinggi mahasiswa jurusan teknik mesin Universitas Brawijaya, misalnya begitu, maka dia bersifat infinite ya, tidak countable. Jadi tingginya 165 cm, dan kita bisa koma sekian ya, 164 cm misalnya. Dan selalu ada di antaranya 165, nanti ada lagi di antaranya 165, gitu ya. Nah, dan karena itu mirip analog ya, disebut analog ya, dia selalu ada di antaranya. Tetapi kadang-kadang variabel random kontinu bisa menjadi variabel discrete ya, variabel random discrete ya. Misalnya tinggi mahasiswa dalam sentimeter terdekat ya, itu dia menjadi discrete ya. 165, 164, tidak ada 164,5 ya. Tetapi kalau kita pengen exact value, nilai yang tertentu, yang exact, maka dia akan bersifat variabel random continue gitu ya. Karena nilai exactnya tentu selalu ada something between ya. Oke. Ada beberapa video ya yang khusus membicarakan variabel discrete dan variabel random yang continue ya, ini yang di link yang pertama ini ya. Ini ada video ya, link yang pertama itu tadi ada video dari Marty Brendel ya. Marty Brendel itu guru SMA di Minnesota sana, Amerika. Udah lama ngajar matematika sejak tahun 2003 di beberapa SMA yang menjelaskan bedanya variabel random discrete dan variabel random continuous. Silahkan diikuti ya, dan video aslinya bisa dilihat di alamat link yang ditulis di atas itu.
In this video, we're going to take a look at discrete and continuous variables and learn the distinction between the two. First of all, let's take a look at discrete variables. Discrete variables are things that are countable. There's a certain number of them. There might be an infinite number, but they're always countable. There's nothing in between. If you have two of them, like for example, the number of markers, well, we could have one or we could have two, but we couldn't have any of those numbers that are between. Remember, there's things like 1.5, 1.25 between there. That would not be discrete, a variable that described the number of markers. And finally, we could refer to it as digital. Think of like a digital clock. A discrete value for time would be like 1042. Well, there's actually more, if we wanted to be more exact in terms of the time, we could have seconds on there. We could have tenths of seconds and so on. But if we just have a digital clock that just has 1042, well, that would be discrete because the next thing would be 1043, and that clock isn't going to tell us anything between there. Now, let's take a look at continuous variables. Continuous variables are infinite, and there's always something in between them. So, for example, if we're talking about time again, then we could look at, well, we have 1042 and 1043. There's actually 1042 and 1 second, 1042 and 2 seconds. Oh, but wait, we could go in between there and say 1042 and 1.5 seconds, 1042 and 1 2/3 seconds, and so on. And there's always a value in between. That means continuous. Think about that. There's no breaks in there. And finally, we can sometimes refer to that as analog, where we have an infinite degree, the exact values. Analog gives us those exact values. And the scale that we choose to work in may change whether it's a discrete variable or a continuous variable. And we'll talk about that as we look at some of these examples here. So, let's take a look. This first one, the number of oranges in a bag, is that discrete or is that continuous? Well, it's countable. How many oranges could be in the bag? There could be 1, there could be 2, there could be 5, but there couldn't be 1.5. So there's discrete values with nothing in between. So this would be an example of a discrete variable. How about this next one? The heights of people in your family. Well, let's think about it. The heights. It depends on the scale that we're choosing. If we go to the nearest inch, for example, well, then it would be discrete. Someone could be 5 feet tall, they could be 5'1", they could be 5'2", and so on. But if we look at the exact values, someone could be 5'1" and 1/4. They could be 5'1" and a half. They could be 5'1", and so on. There's always something between there. So if we're dealing in to the nearest something, so let's say to the nearest inch, then we would be looking at a discrete situation, because we can count all those. There's nothing in between. But if we're going exact, then it would be an example of a continuous situation. So depending on the scale that we choose. How about the ages of your friends? Well, let's think about this. Again, it's a situation where the scale is going to change things, because when we talk about age, many times we talk about years, or for younger kids we talk about months or whatever. Then that scale is going to tell us if it's discrete or continuous. So if we go to the nearest year or to the nearest month, then it will be an example of a discrete, because they're separate values that have nothing in between. So to the nearest something, it would be discrete. And then it would be continuous if we're talking about exact, because remember, someone is born, they could be born at 10:36 and 5 seconds. We could go to tenths of a second to whatever, and then that would give us something that would be continuous. So if we're going to the nearest something, it's discrete. And if we're going exact, then it's going to be continuous. So again, that scale makes a difference. How about this one, the country of birth? Well, countries are, you're either from a certain country or not. So that would be an example where it would be discrete, because you're either from the U.S. or from Canada or from wherever or not. There's not an in-between. Okay? How about winning time in a race? This is another example where depends on the scale. So if we're going to the nearest tenth of a second, that will be an example of a discrete. And if we're going exact, then it would be an example of continuous. And finally, the year of birth. Well, you were born, I was born in 1978. 1979 would be the next year, 1980. Is there anything in between there in terms of those years? Nope. So that would be another example of a discrete situation. So, the difference between discrete and continuous variables: discrete are things that are countable, and they might be infinite. Like, for example, the years would go on and on and on, but there's nothing in between. That's a key piece to be able to pick out the discrete stuff. Continuous, it's infinite, and there's always something between. Depending on our scale can change what exactly we have going on. Oftentimes, we'll think of these as continuous, but if you want to be very accurate and you say we're rounding to something, well, then that would be an example of a discrete. Hope this video was helpful. Keep working hard on your math. You can do it.
Pada slide ya terlihat ya kira-kira bentuk dari kurva distribusi normal atau distribusi Gauss ya. Bentuknya seperti ini ya. Karakteristik dari kurva yang pertama adalah dia simetrik ya terhadap ini min-nya atau rata-ratanya ya. Terus luas daerah di bawah kurva ini total ya adalah 1 atau 100% luas daerahnya. Terus ini kurva bisa diekspansikan hingga ya sampai plus minus tak hingga ya terhadap mu ya. Ini bisa ke sana, tapi tentu semakin jauh dari minnya dia semakin nol, harganya mendekati nol, sehingga kontribusi terhadap luas kurva menjadi kecil ya. Kurva harus bisa didefinisikan hanya dengan min dan standar deviasinya ya, untuk mendefinisikan kurva ini ya. Nanti kita akan mendiskusikan dengan lebih detail fungsi dari kurva distribusi normal ya. Ada video ya dari Josh Starmer ya. Itu dia bersama Joshua Starmer membuat situs atau membuat channel yang namanya StatQuest.org ya, yang berdiskusi tentang statistik dari North Carolina University ya. North Carolina University itu di kota Chapel Hill kalau nggak salah ya. Tentu saja di North Carolina ya. Meskipun namanya North ya, tapi tetap di selatan ya. North Carolina itu di daerah pantai ya, yang timur ya, yang timur ya, artinya berjajar dengan New York ya. Tapi dia agak ke selatan. Ada New York, di selatannya itu Pennsylvania kalau nggak salah. Terus ada Virginia yang terkenal, kemudian di North Carolina ya, meskipun namanya North tapi di bagian selatan, baru di selatan Carolina Selatan adalah di bawahnya lagi kalau di peta. Oke, kita lihat saja video dari Josh Starmer dan Joshua Starmer yang punya StatQuest.org ya. Dengan alamat link ini ya, video yang kedua bisa dilihat di link aslinya ya, tapi bisa juga dilihat di video ini tentang grafik distribusi normal ya, masih belum sampai ke rumus distribusi normalnya.
StatQuest makes me crazy when it's upside down. StatQuest makes me bonkers when it's upside down. StatQuest. Hello, and welcome to StatQuest. StatQuest is brought to you by the friendly folks in the genetics department at the University of North Carolina at Chapel Hill. Today we're going to be talking about the normal distribution. This is part one of a handful of StatQuests on this distribution because it's so darn important. Today, let's just start with the basics. Chances are you've seen a normal or Gaussian distribution before. It's also called a bell-shaped curve because it's a symmetrical curve that, wait for it, looks like a bell. In this example, the curve represents human height measurements. People can be short, average, or tall, or anywhere in between. The y-axis represents the relative probability of observing someone who is really short, or really tall, or who has an average height. For example, it's relatively rare to see someone who is super short, so the bell-shaped curve is relatively low in this part of the graph. But it's quite common to see someone who is close to the average height, so the bell-shaped curve is very tall in this region. And it's relatively rare to see someone who is really tall, so again the bell-shaped curve is relatively low in this region. Here are two normal distributions of the height of male humans when born and as adults. This is the distribution for the babies, and this is the distribution for the adults. The average baby height is 20 inches. The average adult height is 70 inches. Normal distributions are always centered on the average value. Just by looking at the graph, we can tell there is a high probability that a newborn baby will be between 19 and 21 inches tall. In contrast, adults are between 60 and 80 inches tall. You may have noticed that the curve for babies is way tall compared to the curve for adults. This is because there are many more possibilities for adult height than for babies. The more options there are for height, the less likely any specific measurement will be one of them. The width of the curve is defined by the standard deviation. We can tell just by looking at the curves that babies have a relatively small standard deviation compared to adults. The standard deviation for babies is 0.6. The standard deviation for adults is 4. Knowing the standard deviation is helpful because normal curves are drawn such that 95% of the measurements fall between plus or minus 2 standard deviations around the mean. This means that 95% of the baby measurements fall between 20 plus or minus 1.2 inches. And 95% of the adult measurements fall between 70 plus or minus 8 inches. To draw a normal distribution, you need to know 1. The average measurement. This tells you where the center of the curve goes. 2. The standard deviation of the measurements. This tells you how wide the curve should be. And the width of the curve determines how tall it is. The wider the curve, the shorter. The narrower the curve, the taller. The curves then tell us that there is a high probability of measuring a newborn baby boy within plus or minus 1.2 inches of the mean. And there is a low probability of measuring a man within plus or minus 1.2 inches of the mean. Lots of things are normally distributed. We've been talking about height, but there's also weight, commuting times, and many more things. The normal distribution is kind of magical in that we see it a lot in nature. But there's a reason for that, and that reason makes it super useful for statistics as well. Spoiler alert, it's called the central limit theorem. I'm already working on a whole stat quest on the central limit theorem, so that's something we can all look forward to. Hooray! We've made it to the end of another exciting stat quest. If you like this stat quest and would like to see more of them, please subscribe. And if you have any suggestions for stat quests you'd like me to do, put them in the comments below. Until next time, quest on.
Baiklah ya, kita kembali ke kurva distribusi normal dan kita akan mendapatkan fungsinya ya. Nah, kita lihat kurva ada karakteristik yang sudah dibahas sebelumnya ya, simetrik terhadap mean ya, terhadap rata-ratanya dan luasnya 1. Kurva di ujungnya bisa diekspansikan ya sampai mu plus minus tak hingga ya sampai sana, dan dia tidak akan pernah memotong sumbu X ya. Sumbu ininya ya, sumbu X-nya dia bersifat apa itu yang seperti itu asimptotik ya. Dia akan mendekati X tetapi tidak akan pernah menyentuh X ya. Oke, dan satu hal yang kita inginkan ya, harusnya persamaannya nanti didefinisikan hanya oleh nilai rata-ratanya dan deviasi ya, standar deviasi. Ada kuliah menarik ya dari Edward Ken Wu, ini guru SMA di NSW Australia. Saya tinggal agak lama ya di NSW, 4,5 tahun, jadi agak paham ya atmosfer di NSW Australia ya. Ini guru Edward Ken Wu, ini guru leader di NSW tentang matematika ya dan statistik ya. Seorang China ya. Ini perlu juga dicontoh ya. Semakin maju suatu negara itu diversity namanya, itu semakin diterima ya, perbedaan berdasar pengalaman ya. Kalau negara masih berbicara warna kulit, ya, etnis, kemudian agama, ya sulit diharapkan untuk maju ya. Karena berdasar sampel yang kita ketahui negara-negara maju itu diversity-nya selalu lebih diversity, lebih variasi, ras, etnis, agama, dan mereka menerima ya hal-hal itu ya. Saya rasa kita perlu merubah ya paradigma berpikir kita agar kita bisa menjadi negara maju itu ya diversity selalu harus dijaga ya, atau toleransi lah kalau bahasa kita ya, toleransi terhadap perbedaan, dan perbedaan itu sesuatu yang menyenangkan ya menurut saya ya, dan kita harus belajar dari perbedaan itu, seharusnya seperti itu. Baiklah ya, untuk singkatnya kita ikuti kuliah yang menarik dari Edward Ken Wu berikut ini.
The normal distribution. So far, all we've been doing is looking at the numbers of it, right? Like this percentage, that score, all the rest. But so far through this topic, we've actually been dealing with like calculus and stuff, right? And you're like, where's all the calculus gone, right? Well, we haven't been able to deal with any of the calculus because when it comes to this shape, we haven't had anything to integrate. We haven't had the actual function that you can put into an integral, put in boundaries and all the rest, right? So that's what I'm going to unpack for you right now, and it's dealing with this function is what's going to be tomorrow and Friday's lesson, okay? So remember what the probability density function is. This is all stuff from that piece of paper that I gave you the other day, right? These are the three qualities that the probability density function has, and what we're going to try and do is almost like guess who. Like we're going to try and work out what's the function that makes sense of all of this, that has all of these characteristics, right? Now, we have lots of different functions. These are all the functions that you learnt about in graphing techniques, plus a little bit more, actually. Like you can graph, with some help, even if you're not very familiar, you can graph all of these, okay? So I want you to have a think about which of these would be closest to something like the probability density function shape that we've been dealing with, the normal distribution, okay? Now, there's a lot to play with here, so I'm going to try and narrow it down for you, okay? Remember how I said this is kind of like guess who, okay? You know how there are some questions that you should ask early on, like, is the person male or female? Or do they wear glasses? Or have they got hair, right? So there are obvious questions to ask. The most obvious question out of these three to look at is this guy right here. You know how it sort of levels off and then it's got asymptotes horizontally, right? I want you to think about these 6 families of functions and which of them have horizontal asymptotes versus which that don't. Have a think. Okay, so maybe some of you are thinking, okay, which ones do and which ones don't? Do you agree with me that we can really quickly say all of these guys, they're all duds? Do you see that? Polynomials are like straight lines, parabolas, they don't have horizontal asymptotes. In fact, they don't have asymptotes at all. Absolute values are the same. Logs do have asymptotes, but not horizontal ones. They have vertical ones, okay? Trig functions, I mean, you've got sine and cos, they don't have asymptotes. Tan's got asymptotes, but which way do they go? They go up and down. So they're also, yeah, they're vertical, okay? So that leaves us with these two. Rational functions, like something divided by something, and then exponentials. Now think with me, maybe it's been a while since you've had a look at it. Do you remember like rational functions? They look like this. Do you remember? Yeah, the hyperbola, very good, our old friend, okay? Now the problem with every rational function is not only do they have the horizontal asymptotes we want, but, have a look at it, it's also got vertical ones, and this has no vertical asymptotes. Do you see that? Okay. So all that leaves you with is the exponential function. This is the only one we can work with. Except, just look at it for a second, right? It doesn't look anything like this, does it? Right? Well, now, very good, right? So part of it does, but part of it doesn't. Like you've got this part over here, which has that horizontal asymptote behavior. That's the part we want, right? And then you have this right-hand side, you're like, that's no good, right? I don't want the right-hand side to do that skyrocketing thing. Does that make sense? Okay. So how do I fix this? Well, have a look at the x values that work for us. Do you agree the good x values are the negative ones, right? The negative x values, they're good. The positive ones, no good. What knowledge do we have? What concept do we have that can fix numbers so that they're always positive or negative? What do we call that? We call absolute value, right? Now, normally we would say, you put the absolute value signs around it, and what does that mean? Absolute value means always positive. But I don't want the positive side, I want the negative side. So here's what I'm going to do. I'm going to put a minus sign at the front of my absolute value. Are you with me? See what's going on there? Okay. So this is better. It's got that dual asymptote thing, okay? But then you've got a problem. We've solved one problem, but we've created another one, right? Look closely with me. Is this what we want? No. It's not, right? See how it's sharp, right? It's sharp there, and that's no good. We have a name for this kind of point. It's called a cusp, C-U-S-P, okay? Oh, yeah. You're like, I don't want this, okay? I don't want it to be sharp there. I actually want it to be, look at the normal distribution. I want it to be, we have a word for this. It starts with S. What's the, stationary. We want it to be stationary, not sharp, okay? Now, we shouldn't be that surprised that trying a trick like this makes it sharp, because this is what the absolute value of, or negative the absolute value of x looks like. It's sharp, right? So what I want is something that looks like this but isn't sharp. Something that's concave down, sort of, right? But it's sort of gentle, right? What do I want that would do that? And the answer is a shape that you guys know, right? An upside down parabola would do that, right? Do you see? It's always negative. That's what we wanted. And also it's gradual there. Does that make sense? So have a look at what happens when we put this guy in the index. Just take a look at that. Oh. That's pretty good, right? That's pretty good, okay? Now, hold on. We're not quite done yet. We're not quite done. Because look, we know, just going back to the properties of the normal distribution, that the center, right, the symmetry of it should be where? Think about it. It's on the diagram, right? It should be centered around the mean. Now, this would be fine if your mean was 0, but like your mean's not usually 0, right? It's some other number, okay? What knowledge do we have to be able to move this thing so it centers somewhere else? What would I do? Sean? Okay, there's going to be a constant. Where am I going to put it? I've got to put it with the x, right? Because I want to move it left and right. Does that make sense? So this is what we do. You see how it's the same thing you were looking at before, but you've got that minus mu in there, which moves it over. Does that make sense? Okay, so you're like, aha, now we're talking. Okay? All right, now, stay with me, 12. Shh. We are almost there, I promise. Okay? This guy here is very close to the normal distribution. The only difference is we don't know how far spread out the thing is or how tall it is, okay? So just hold on to your hats, and I am going to ask you to pick up your pens at this point, right? In order to take this guy, which is basically the right function, and get the scale right, we have to add in stuff to do with the standard deviation, because that tells you how stretched out this thing is, okay? So I know it looks gross, but compare it to what we've got here, okay? This is the real equation. Okay? Now it looks nasty, right? Can you write this down, please? This is essential. In fact, I'm going to write it down too. Shh. Now, we're going to write this down together because I know it looks like a garbled mess, and so we're going to try and make it a little bit better. That's what we're going to do right now. Okay? No. This guy is not on the formula sheet. I will tell you why in a second. Because we never need to use it. But for now, I want to work with this function. Okay. Now the first thing is, let me just go back one slide. Right. You've got it. If you haven't written it off the screen, just write it off the whiteboard. Okay. I can't go back because I'm recording. Never mind. Okay. The difference between this and what you were just looking at. In fact, I'll write down. Right. The other function we were looking at before looks like this. This is what we were looking at, right? Now just have a look at the difference. I know it looks very scary and intimidating, right? This guy comes into the denominator, right? And then this guy comes out to the coefficient, okay? The key thing I want you to see is it's to do with sigma. It's to do with how spread out your data is, okay? Now, this thing looks gross, so I'm kind of on a mission to simplify it. And we can, because I want you to look closely at the index. Look at that garbled fraction up in there, right? It's not a joke. I wonder if that thing in the index looks at all familiar from what we've been looking at this week. Doesn't it look a whole lot like the equation for a z-score, right? The equation for the z-score is it's x minus mu all divided by sigma, right? Which you've got all the pieces there. So here's what we're going to do, okay? In your book, here's how we're going to simplify this thing, okay? This guy out the front, it just stays put. It's fine. But I want to rewrite this index to make it a little more obvious that I can see the z-score in there, okay? For starters, see how there's a minus and then there's a 2 on the bottom. None of them appear in the z-score formula, so I'm going to pull them out. Okay, so I get this, minus a half, and then you get left with x minus mu squared on sigma squared. Do you agree with that? So I've broken the fraction into 2. It looks gross, but just have a look at the second fraction. Yeah, that's a multiplication, yes. Okay. Have a look at this second fraction. Do you agree that basically I can take out this squared thing, right? The top squared, the bottom squared, so the whole thing is squared. Does that make sense? But look, this guy is, that's the z-score. Right there. That's the z-score, okay? Now, if you haven't written down up to this point, that's okay. Just put your pens down for a second because I'm about to do 3 things all at once and I don't want you to miss them, okay? I'm going to highlight them all in colors so you can see what's going on. And this is going to be really weird, I'm going to do it right to left because I think that's going to be the most sensible order to do it in. Okay, stay with me. I've got this e to the negative a half, and then I've just said that this is z. Do you agree? That's the formula for the z-score. So the first thing that changes is that turns into a z squared. Is that okay? Then, if you have a look in here, have a look at this fraction out the front, right? 1 over, now sigma, right? Standard deviation. Have a look over at my normal distribution. On a z scale, the standard deviation is by definition just 1, right? You see that's the distance from one standard deviation to the next, it's just 1 every time. So instead of writing 1 over sigma this, I can just write 1 over 1 root 2 pi. Does that make sense? You see how I've substituted that sigma over there? Now the last thing I need to do is, see how we started by saying this is a function of x? Oh. This is not a function of x anymore. There are no more x's. What's this a function of? It's a function of z, right? So now I've done all changes. Now you can pick your pen back up again, right? This is the line. In fact, I'm going to write it with proper colors, and I don't need to write this 1. Doesn't change anything, right? Our probability density function we can write as 1 over square root of 2 pi e to the negative 1 onto z squared. I know it's still not beautiful or simple, but it's better. It's better than what we started with, okay? And this really will be the version that we use going forward, okay? Because it's better than that guy, all right? Now, I know this looks terrible, okay? But I want to give you... You have to find the beauty in it. Well, this is the thing, right? Here's my pitch for you, okay? In 2 minutes or less. This is beautiful because it fits every single thing that we wanted about the normal distribution. It's got the symmetry, it's got the right location, it's got the right size. Even though it is complicated, it does everything I want it to, okay? The only catch is, when you have a look at this guy, right? What do we generally do with probability density functions? Like, how do I find a probability? How do I find variance? What's the thing I do after this? I integrate, right? I integrate. Now, if you look at this and think, gross, I don't want to integrate that, then that's the right instinct, because I'm going to show you what happens if you integrate. The probability density function, what do we call it when you integrate the PDF? You get the, do you remember? The CDF, the cumulative distribution function. Don't write this down, don't panic, but this is the cumulative distribution function, okay?
Why did you show me that?
Now I'm showing it to you because, thankfully for us, we never ever need to use this, okay?
I'm excited. Why is there an exclamation mark?
You're wondering why there's an exclamation mark there. It's a piece of mathematical notation,
No, it's not.
okay? It's called the factorial. It's called the factorial, okay? Now, we're right on the bell, so over the next 2 days, Thursday, Friday, what we're going to do is, since we don't want to do this, what's the alternative? There are 3 alternatives, and that's what we're going to do on Thursday and Friday.
Ini adalah persamaan distribusi normal ya, atau biasa disebut juga dengan distribusi Gauss ya. Kita akan mendemonstrasikan ya persamaan ini menggunakan Excel ya. Oke. Pertama kita buat rata-rata, kemudian standar deviasi, misalnya rata-ratanya ini 10, standar deviasinya 1, ini X-nya, ini fungsi X1 misalnya 0, ya, sama dengan kita buat incrementnya 0,1. Ya, sebenarnya semakin kecil semakin baik, tapi tentu diperlukan usaha atau proses penghitungan yang lebih sulit ya, atau lebih berat paling tidak, jika kita menggunakan increment yang lebih kecil. Fungsi X-nya adalah kita mengikuti ini, seper sigma akar 2pi ya, atau ini kita rubah dulu biar simbolnya sesuai. Insert simbolnya mu rata-rata, terus ini juga kita ubah. Nah, simbolnya kita ganti dengan standar deviasi sigma. Nah, maka ini adalah seper, apa tadi rumusnya, bisa dilupa. Sigma akar 2pi sama dengan sigma, ini kita kunci barisnya biar tidak berubah barisnya kalau di copy, dikalikan 2 akar ya, akar 2 kali pi ya, pangkat -1 karena seper. Oke, terus kemudian dikalikan eksponensial apa tadi? Eksponensial sec X kurangi mu kuadrat min ya. Ini min X ya, ini kita kunci kolomnya ya, X kali kurangi mu, ini kita kunci barisnya kuadrat iya min, kemudian kita bagi dengan 2 sigma kuadrat, 2 kalikan sigma, sigmanya kita kunci barisnya dikuadratkan ya, gitu ya. Tinggal kita copy. Nah, maka kita dapatkan grafik dari distribusi normal harusnya. Oke, kita buat aksisnya 0 sampai 20 saja. Terus ini kita pindahkan ke sini biar cepat kelihatan. Nah, seandainya kita punya, kalau mu-nya yang berubah, misalnya 12 ya, ininya tetap 1, di sini kita punya fx2 misalnya, yang kedua, ya ini tinggal copy saja toh, kita sudah kunci-kunci tadi, ya Sekarang kita tambahkan datanya di sini. Select data, add. Sekarang kita tambahkan fx2. X-nya kita pilih yang ini. Sama X-nya, cuma Y-seriesnya kita pilih yang fx2 ya. Oke ya. Oke, ini dia cuma bergeser pusatnya ya. Terus kemudian kalau yang berubah standar deviasinya misalnya 2 gitu ya, maka kita tentu bisa kopikan ke sini ya, terus kemudian kita tambahkan fx3. Oke. Nah, kita perbesar. Kemudian kita pilih select data. Kita tambahkan namanya adalah fx3. Data X-nya adalah sini, tetap. Kemudian Y-nya adalah yang ini ya. Oke. Oke ya. Kita nggak keluar. Ada yang salah nih. Ulangi lagi, select data. Ya, kita hilangkan aja dulu. Tambah. Ini, kemudian X-nya ini. Pusing Excel-nya. Oke, seharusnya saya tidak. Ini ya ada 3 ya. Ini adalah yang standar deviasinya 2, dia turun seperti ini ya. Tingginya, tetapi luasnya ini tetap 1 ya. Begitu. Kita belum menghitung luasnya, ini masih menggambarkan grafiknya. Bagaimana menghitung luasnya? Luasnya ya seperti kita mengetahui, kita bisa menggunakan konsep dari kalkulus, yaitu luasan adalah integralnya fx dx. Itu adalah kita bisa mendekati dengan luasan pias-pias kecil ini. Semakin kecil dx-nya, ya, semakin dia mendekati kurva sesungguhnya. Ya, mungkin ada sedikit kalau dx-nya tidak cukup kecil, mungkin ada sedikit perbedaan ya. Oke. Kita akan coba menghitung luasnya ya di sini misalnya. Kita hitung yang warna biru saja ya. Kita atau masukkan 2 kolom aja. Yang di sini tentu A increment, ini A totalnya ya. A increment rata-rata 2 ini dibagi 2 ya, dikalikan lebarnya ya kan. Ini ditambah itu dibagi 2 dikalikan lebarnya 0,1 ya dalam hal ini. Ini adalah luas sebuah kotak di sini ya. lebarnya increment, tingginya adalah tinggi rata-rata antara tinggi sebelah kanan dan tinggi sebelah kiri. Oke, ini kita bisa kopikan. Nah, totalnya tentu jumlahnya ya. Ya, sama dengan ini ditambah dengan sebelah kirinya itu. Kita bisa kopikan, harusnya 1 luas totalnya ini. Nah, ya kan? Luas totalnya sama dengan 1. Luas total daerah tertentu ya kita bisa merubah-rubah ini, batas atas dan batas bawahnya. Kalau ini dari 0 sampai 20 ya. Nanti kalau diinginkan luas total yang lain, ya kita bisa menghitung dengan merubah-rubah Excel kita ya. Misalnya ya, ada beberapa hal ya yang perlu diketahui tentang kurva normal ya. Saya siapkan dulu untuk menulisnya. Mana ya? Ini. Jadi luasannya ini yang perlu diketahui. Luasannya ini misalnya, berarti ini kita bagi 3 ya. Ya, ini antara mu plus sigma dan ini mu plus min sigma. Mu min sigma. Luasannya itu ada rumus 68, 95, 99 ya. Ini luasannya yang merah 68,269% ya. Terus kemudian luasannya di sini yang hijau, berarti ini mu plus 2 sigma mu plus 2 sigma sampai mu min 2 sigma. Luasannya adalah 95,45 ya, 45%. Kemudian luasannya mu plus 3 sigma sampai mu min 3 sigma. Ya, ini adalah 99, hampir semua luasannya terletak antara mu min 3 sigma dan mu plus 3 sigma. Ya, 0,73, tidak perlu dihafalkan ini ya, angkanya boleh dilihat. Nah, tentu sisanya adalah dibagi 2 ya, di kiri dan kanan itu. Ya, sisanya di sini ya kurva asimptotik. Nah, itu ya 0,135%. Yang kanan dan ini juga yang kiri kanan ini 0,3 kan, 0,135%. Biasanya ini disebut daerah tolak. Maka ini kita bisa ya antara keep ya, kita bisa demonstrasikan di Excel kita mulai min sigma sampai mu plus sigma ya. Ini Excel kita tadi ya, ini kita hilangkan saja yang 2 dua kolom terakhir ini kita bisa menjumlahkan antara 9 sampai 11 ya. Ini jumlahnya adalah 0,6822 ya, mendekati ya. Kalau pengen lebih dekat lagi, ya increment-nya kita buat sedikit lebih kecil ya. Semakin kecil ya semakin bagus, tetapi tentu perlu komputer power yang lebih besar juga ya diperlukan. Misalnya ini sekarang tidak tambah 0,01 tetapi ditambah increment-nya ini 1/100 ya. Di sini kita copy ya, maka totalnya seharusnya semakin mendekati 8 sebentar, ini dikalikan increment ini ya, salah yang ini masih dikalikan 0,1, ini harusnya dikalikan dengan lebarnya yaitu increment, kemudian kita kunci ya. Kita lihat di sini totalnya mendekati 68,269 ya. Ini masih 2685 karena masih belum kecil, mungkin ini harus dikecilkan lagi, tapi kita anggap cukup ya. Seandainya 68,269 tadi kita mau menghitung sampai mu min 2 sigma berarti 8 ya, dari 8 sampai 12 ini yang di situ. Yang sini 8. Nah, tapi kurang ini sampai 12. Ya, kita harus perlebar lagi. Oh, masih belum. Ya, ini sampai 12 ya, ini 95,4498 atau 95,4498% ya. Kita lihat di sini 9,45 ya, mendekati lah. Kalau mu min 3 alpha berarti mulai 10 dikurangi 3 alpha 7 sampai 13 ya. Ininya diganti 7. Ya, ini harus sampai 13. Nah, masih belum. Nah, belum. Nah, ini totalnya 0,9973 ya. 99,73 ini tinggal sisanya ini yang 0,135 di sisi kiri dan 0,135 di sisi kanan. Selain kita menggunakan Excel ya, yang kita bangun sendiri seperti ini, kita bisa juga menggunakan ya, Wolfram Alpha atau online kalkulator definite integral ya. Ini yang Wolfram ini, Wolfram Alpha widget ini bisa kita gunakan untuk menghitung luasan atau integral. Ya, kita fungsinya ini seper sigma pangkat 2pi, tapi sigmanya dimasukkan ya. Sigmanya 1 kalikan akar 2pi, 2 kali pi. Ya kan? Pangkat min 1. Min 1 kalikan eksponensial dari min. X min mu, min X min rata-ratanya 10, ya kan? X min mu kuadrat, ya, terus kemudian dibagi dengan 2 sigma kuadrat, dibagi dengan 2 kalikan sigma kuadrat, sigmanya 1 ya, 1 kuadrat. Ya, dari berapa tadi? Kalau 9 sampai 11 ya, min sigma dan sampai plus sigma. Submit. Nah, ini kita bisa ngecek ini benar juga ya persamaannya. X min mu ya benar ya, eksponen dibagi ini sudah benar dx. Nah, kalau pengen lebih more digit juga bisa. Nah, ini lebih lengkap lagi. Kita juga bisa dari 8, ini mudah nih, 8 sampai 12. Ya, tinggal ganti ininya loh, ini langsung 0,95,45. Terus kemudian ini 7 sampai 13, ini 9 harusnya. Ya, 0,9973. Kita lihat di gambar kita tadi. 99,73 ya, benar. Oke, kalau sampai tak hingga ya sayangnya kita tidak bisa memasukkan angka tak hingga. Ya, kita bisa memasukkan angka yang cukup kecil ya, misalnya 10 dikurangi 100, ya 90 min. Terus 10 ditambah 100, ini 110. Kita anggap ini sudah tak hingga. Ya, kita lihat, mungkin agak lama ya. Ya, mendekati 100% luasannya. Dari min tak hingga hingga tak hingga. Begitulah ya interpretasi dari kurva normal ya, menggunakan Excel berserta grafiknya. Kita juga bisa menggunakan Wolfram Alpha kalkulator ya. Ada kuliah menarik berikutnya ya dalam bentuk video dari kuliah berikutnya. Silahkan diikuti dari alamat link ini disediakan oleh Julio Gonzalez yang kita sudah melihat beberapa video sebelumnya ya, tentang dia yang punya channel organik semester tutor itu ya. Julio Gonzalez itu lulusan University of California Los Angeles ya, terus kemudian dia tinggal di Los Angeles masihan dan membuat channel organik semester tutor. Begitu kira-kira ya. Nah, silakan diikuti link ini yang seperti biasanya Julio Gonzalez kalau membuat film detail ya, dan ada contoh-contoh soalnya. Mudah-mudahan bermanfaat.
In this video, we're going to talk about the normal distribution or the bell-shaped curve. So let's begin by drawing a picture of that curve. And it's going to look something like that. Now, right in the middle, we have the population mean, represented by the Greek letter mu. And to the right of that, one standard deviation away, we have the Greek letter sigma. And this is one standard deviation to the left of the mean. And then this is two standard deviations away. And then 3 on both sides. All the way to the right, we have infinity, and all the way to the left, negative infinity. Now, the area under the curve represents the probability of an event happening between 2 points. So the probability of an event happening between the mean and the first standard deviation, you can calculate it if you know the 68, 95, 99.7 rule. So within the first standard deviation of either side from the mean, there's a 68.268% chance that an event will happen in this region. And then within two standard deviations, the percentage is 95.45%. And then within 3 standard deviations of the mean, the percentage is going to be 99.73%. Now, I hope that you're taking notes because you're going to need to know these numbers. It's going to help you solve some problems that are coming up soon. Now, if we take this number, 68.268, and divide it by 2, that's going to give us 34.134%. So that's the percentage of finding an event between the mean and the first standard deviation. Now, the left side is going to be the same. It's going to be 34.134%. When you're dealing with a normal distribution curve or bell-shaped curve, you can have symmetry in this problem. And keep in mind, the area of this region is 0.34134. It's the percentage as a decimal. So the area is going to be the same as the probability of an event happening within a certain region. Now, what percentage goes in this region? If you take the difference between these two numbers, so if you subtract 95.45 by 68.268, that will give you 27.182. Take that number, divide it by 2, and you should get 13.591. And this number is going to go on both sides. So that's the percentage of an event happening between the first and the second standard deviations of either side. Now, to find the next number, follow the same process. So we're going to subtract these two numbers. 99.73 minus 95.45, that's 4.28. Then divide it by 2. So the percentage in this region is going to be 2.14%. And the same is true in that region as well. Now, to find the percentage that goes in those two regions, keep in mind the total percentage from negative infinity to infinity is 100%. So take 100 and subtract it by 99.73. You should get 0.27. And when you divide that by 2, the answer in this region is going to be 0.135%. And the same is true for this area as well. So you may want to take a picture or at least write this down because you can use this to solve problems associated with the normal distribution curve. Now, it's important to keep in mind that mu represents the population mean. And sigma is the standard deviation. Now, as we said before, the probability of an event happening from negative infinity to infinity is 100%. That's the total probability, which means that the total area of this curve is 1. So if you add up all of these numbers, you should get 100%. And the left side, everything up to here has to be 50%, which is 0.5 as a decimal. So now let's work on some practice problems. Number 1, the test scores of a physics class with 800 students are distributed normally with a mean of 75 and a standard deviation of 7. Part A, what percentage of the class has a test score between 68 and 82? So feel free to pause the video and work on this problem. Now, what I'm going to do first is I'm going to draw a picture that's similar to the picture that I had before, but instead of using symbols such as mu and sigma, I'm going to use numbers. Now, we said that the mean is 75 and the standard deviation is 7. So the first thing I would recommend doing is put in the mean right in the middle. Then one standard deviation away from the mean, we're going to put the numbers as well. So we're going to add 7 to 75. 75 plus 7 is 82. And 75 minus 7 is 68. Now, let's move another standard deviation away from the next number, from 82 and 68. So 82 plus 7 is 89. 68 minus 7 is 61. Now, let's do it one more time. 89 plus 7 is 96. 61 minus 7 is 54. Now, we could stop here. Now, let's put the appropriate percentages in each region. So we know that within the first standard deviation, it's going to be 34.134%. And then between the first and the second standard deviation, it's going to be 13.591%. And between the second and the third, it's going to be 2.14%. And then for this region, 0.135%. So now we have everything that we need in order to get the answer. So let's calculate the probability, or the percentage, of the class that has a test score between 68 and 82. So x is going to be a random continuous variable that can vary beyond 75 or less than 75. Now, all we need to do to get the answer is basically find the area under the curve between these two numbers. So we got to find the area of the shaded region. So all we need to do is simply add up the percentages between 68 and 82. So it's going to be 34.134 plus another 34.134. So that's going to be 68.268%. So that's the percentage of the class that has a test score between 68 and 82. Now, there's a formula that you could use to get the same answer, in fact, a more accurate answer, using calculus. Now, if you're watching this video and if you haven't taken a calculus class, don't worry about it, because the formula that I'm going to show you, you can easily use it with the appropriate calculator. And if you don't have a calculator, I can show you how to use it with an online calculator at Wolfram Alpha. So here's the formula that you need. The probability of finding an event between A and B is going to be the definite integral from A to B. E is the inverse of the natural log function, and then raised to the negative x minus the population mean squared divided by 2 times the square of sigma, or the standard deviation. And this is all divided by sigma times the square root of 2 pi. And then we have a dx symbol here. Now, all you need to do is plug in the population mean, which you have, that's 75, you also need to plug in the standard deviation, which is 7, and then plug in A and B. In this case, A is 68, B is 82. And then just type that into the calculator, and that should give you the answer. So let's go ahead and do that. So the percentage of students with a test score between 68 and 82 is going to be the definite integral from 68 to 82, and then it's going to be e raised to the negative x minus 75 squared divided by 2 times 7 squared divided by 7 times the square root of 2 pi dx. So make sure to use these parentheses that I'm showing you when you're plugging into your graphing calculator. I'm going to show you how to use Wolfram Alpha towards the end of this video, so you can look for it then. So let's go ahead and plug this in. It's going to take me a while to type this in, so bear with me for one moment. And it's going to take a while for the calculator to get the answer too. So what I got is 0.68268949. So if you multiply that by 100, that's going to be 68.268949%. So as you can see, these two answers are not exactly the same, but they're close enough. So this is an approximation, and this answer is more accurate to the exact answer. So technically it should be like 68.269 instead of 268. But if you round it to 68.3, then you should be fine. Now let's move on to our next problem, or the next part of this problem. That is part B. Approximately how many students have a test score between 61 and 89? So we're not looking for a percentage, but rather the number of students. And keep in mind, we have a total of 800 students in this class. So first, let's find the percentage as we did in part A. So the percentage of students with a test score between 61 and 89 is going to be, so we're starting at 61 and we wish to end at 89. So we need to find the area under the curve for that entire region. So basically we need to add those four numbers. So we're going to add 13.591 plus 34.134 plus 34.134 again, and then another 13.591. And you should get approximately 95.45%, because these two numbers, they're within 2 standard deviations of the mean. So that's always going to be about 95.45% whenever you have that situation. Now let's confirm this answer with a calculator. So we're going to evaluate the definite integral from 61 to 89, and then it's going to be e raised to the negative x minus 75 squared divided by 2 times 7 squared divided by 7 times the square root of 2 pi. So notice that this portion doesn't change, because the mean and the standard deviation is the same for part A and B. The only thing that's changing is the limits of integration, A and B. That's all we need to change in this problem. So go ahead and plug that in. If you don't know how, I'll show you later at the end of this video. calculator takes about 5 seconds to get the answer. So I got 0.954499736. So that's approximately 95.44997% if you multiply this by 100. So this answer is more accurate, but nevertheless, this is a good estimate of this answer. It rounds pretty well. Now, this is not the final answer for part B. So what this means is that 95.45% of the class has a test score between 61 and 89. Now, there's 800 students. So what's 95.45% of 800? So what I'm going to do is take this number, because it's a more accurate value, and multiply that by 800. My calculator also has a 1 here. So if you take that number and multiply by 800, it's going to give you 763.6 approximately. Now, because we're dealing with people, we want to round to the nearest whole number. So we're going to say approximately 764 students have a test score between 61 and 89. So this is the answer to part B. Now let's move on to part C. What is the probability that a student chosen at random has a test score between 54 and 75? So go ahead and work on that problem. So here's 54, and we're going to stop at 75. So basically, we need to add these three numbers. So the probability of selecting a student that has a test score between 54 and 75 is going to be, so we're going to add 2.14 plus 13.591 plus 34.134. And so you should get 49.865%. So that's an approximation, pretty much a good approximation. Now let's get the exact answer, or a more accurate answer, using calculus. So this is going to be the definite integral from 54 to 75, e negative x minus 75, let's not forget to square that, divided by 2 times 7 squared. That's a terrible looking 2. I gotta fix that. Divided by 7 times the square root of 2 pi dx. And so I got 0.498650102, which is about 49.865% if you take this number and multiply by 100. So this is a very good approximation. And so that's the answer for part C. Part D, the last part of the problem. Approximately how many students have a test score greater than or equal to 96? So using the graph, what's the answer? So all we need is this region, which we can clearly see that it's 0.135%. Now, we're not looking for the percentage, but the number of students, which we'll get to later. So how can we get the same answer using calculus? So we know we need to calculate the definite integral from a to b. Now we could see that a is 96, but we only have one number here, so what's b? What should we put for b? Now, if you're thinking of 100, you shouldn't use that. Because granted, most test scores are graded based on 100%. Like the highest value is 100, but sometimes teachers may have extra credit. So some students could have a score of 105 or 110. If you put 100 here, you won't get 0.135%. Let's call the function f of x instead of writing the whole thing. But I'm going to plug it in. So give me 1 minute to do that. And so if you integrate it from 96 to 100, you're going to get 0.00117238. So if you multiply that by 100, that correlates to 0.117% approximately, which is not the same as this answer. So what you need to keep in mind is that this goes to infinity, and the left side goes to negative infinity. So you have to integrate it from 96 to infinity. Now this is going to be a problem because for the most part, we can't plug in infinity into a calculator. So we can approximate the answer by picking a number that's... I need to get rid of this. We need to pick a number that is very high that can represent infinity. So 100 wasn't good enough. So let's pick a much bigger number like 1,000. Now the answer won't be exact, but it's going to be a very, very good approximation. So if you go ahead and plug this in, you should get an answer that's very, very close to this answer. So go ahead and type that into your calculator. Now my calculator gave me this answer, 0.0013498903. So multiply that by 100, and that's about 0.134989, and I'll stop there, percent. So this rounds to 0.135%. So that's a good approximation. Now, let's determine the number of students that have a test score that's equal to or greater than 96. So we're going to take this number and multiply it by the number of students in class, 800. So 0.0013498903 times 800. You should get 1.0799. And so for this, we're going to round it to the nearest whole number. So approximately one student scored a 96 or more on his physics exam. So that's how you can use the normal distribution curve to answer problems such as this one. Now go ahead and open up your internet browser. I'm going to use the Google search engine. And then when you're ready, type in online calculator, definite integral. And then you can also type in Wolfram Alpha. So I'm going to go to this site, Wolfram Alpha Widgets, Definite Integral Calculator. And you should see a page that looks like this. So type it in exactly the way I'm going to show it to you. So type in E, and then Shift 6 to get the arrow, negative, parentheses. If you don't put the negative sign, you will get it wrong. X minus 75 squared, that's Shift 6. And then we also need to open up another parentheses in front of the negative sign. So you need to open up two parentheses, keep that in mind. And then divided by, open a new parentheses, 2, Shift 8, that's the multiplication symbol, times 7 squared. Close parentheses and close it again. This entire thing has to be on the exponent of E. That's why we have to open up an additional set of parentheses. And then divided by, open a new set of parentheses, 7 square root SQRT, open parentheses again, 2 pi, 2 pi, and then close the parentheses twice. Now we're going to integrate it from 68 to 82, and then click submit. So you could see the answer here, 0.68 68.2689. So that's about 68.269% if you multiply it by 100. Now the good thing about this is you don't need to type in the integral expression because that part is not going to change. The only thing you need to change are the limits of integration. So for part B, we need to find a probability from 61 to 89. So let's change these numbers and then just click submit. And so we have 0.9545 or 95.45%. If you need more digits, click the more digits link here, and then you can get a more accurate answer, which we had 0.9544997. And if you want more numbers beyond that, you can write to your heart's pleasure. Now let's move on to part C. So it was from 54 to 75. And so we did get this answer, 0.49865. And to see a more accurate answer, 0.4986501, and we rounded to 02. At least my calculator did that. But we can leave it as 0.49865, or 49.865%. Now for the last one, now I mentioned not to integrate it from 96 to 100 because it won't give you 0.135%. You need to go to infinity. So as you can see, 0.00117. So this is not an accurate answer. But as you increase this value, let's say to 105, it's going to approach a more accurate answer. Notice 0.00134. So it's getting close to 0.00135. So let's try 110. Now, notice that its conversion is getting closer to 0.00135. So we'll need to pick a large number that represents infinity. So we can try 1,000. So we get 0.00013499. And you can select more digits if you want. Now, let's pick a number that's bigger than 1,000 to see if it's going to stay at this value, if it's going to converge to it. If the value changes, then we don't have the right answer. So if we go to 10,000, it might take longer to calculate. Notice that this number didn't change. Wow, it's loading. I guess it takes a longer time to go up to 10,000. But you can still round it to 0.00135. So if we go to 100,000, it won't change. That means your final answer is, if you multiply this by 100, 0.135%. Because 100,000 is a good approximation of infinity. And so that's it for this video. Thanks for watching.
Demikianlah ya kuliah panjang dari distribusi normal ya. Juga dibantu dari video yang saya peroleh dari channel YouTube dari Marty Brendel di Minnesota dan juga Josh Termer ya, dari North California University dengan start quest-nya. Kemudian ada Eddie Wu dari New South Wales. Dan favorit kita, Julio Gonzalez dengan channel Organic Chemistry tutornya di Los Angeles. Mudah-mudahan dengan kuliah panjang tersebut ya pemahaman tentang distribusi normal ya dapat diperoleh dengan baik.